Swayam Prabha. Digital India. Educated India.
So, thank you, Lord Raj, Sanjay, and the team for making me part of this beautiful gathering, celebrating the scientific contributions of my very good friend, Professor Satyamurthy. Professor Satyamurthy joined IIT Kanpur when he returned from Toronto from Polanyi's lab, and I have been a very, very great fan of his work. So Professor Satyamurthy joined IIT Kanpur in 1978 from Polanyi's group in Toronto, and he started bringing in new discipline to theoretical chemistry milieu in India. And all of his co-travelers for the almost like half a century now, this is my felicitation to him for his 75th birthday, have wonderful things to say in their own way, in their own experience. My personal felicitation to him would be just to say that thank you, Sati, for keeping the dream of our community alive in India, which we very proudly note now that it has been passed on to next and the next generation, which also includes your students and grand students. No gathering of theoretical chemistry in India, and I'm sure most of the gatherings in their specialization abroad will not have one of them presenting their work, which is something very, very exceptional that has happened to our country in the theoretical chemistry scene. And we are therefore ready for any new technological development that comes in, including algorithm or any other technological support, that we can always use them to advance our knowledge in this discipline in our own specialization. So thank you once again, Sati. Thank you. So, well, I am going to be talking about the simplest of the atomic systems, and that is the hydrogen atom. But before I do that, let me just give a brief introduction that most of the chemists always talk about the structure and properties relationship. Structure, property relationship. Now, Walter Cohn and Hohenberg put it very nicely long time back in 1964 in terms of the first HK theorem of the foundational density functional theory at that time, at least for the ground state. And that was that external potential defines the Hamiltonian, Hamiltonian defines the wave function, and all the properties can be defined. He also asked the reverse inverse question and showed in the theorem 1 that the density has a unique mapping to the external potential to within a trivial constant for the ground state, which paves the way for doing the structure property relationship not just on the wave function or external potential, but straight from the ground state density. I'm not confining myself to the ground state density. One can expand it later on in details. So, and there were some very, very fundamental initial work done on densities. Thomas Fermi is one which Manoj will be talking about. Well, started almost similar to the wave functional theory. Now, the theorem that I'm mentioning is known as the Kato-Cusp condition, which is on the wave function. It's a spherical average of the wave function. Take the derivative of that with respect to any interparticle distance in the Coulomb system. My concentration will be on the electron nuclear distance, so that I will take the interparticle distance to 0, and that is called the Cusp condition. So log derivative of wave function is minus z. So one always understands this in terms of the DFT kind of understanding in a very simple-minded manner, that the density has two information already. One, the identity of the nucleus, and where the log derivative becomes equal to the nuclear charge. For density, it becomes minus 2z. Okay, because wave function is minus z, density is minus 2z. So log derivative of density at the coalescence point of internuclear distance is equal to minus 2z. So not only the density not only has the information about the location of the nuclei, which will decide the external potential, but also the identity, which will completely decide the external potential, giving you the Hamiltonian, giving you thereby everything else that I just talked about. Now, what about situations where you do not have the possibilities of applying this cusp condition, in the sense that the derivative of the density is 0 at the nucleus, or the wave function is 0 at the nucleus. Even in this case, the Schrodinger equation is equally valid, but you do not extract the information on the nuclear charge and the location. Equation is valid, the cusp condition is valid, but you are not able to extract from the density. So we introduce something called scale density. So what we do is, we take the wave function, divide by r to the power L. I'm talking about the spherical systems. And then I do the density, where the density in the one electron density is now divided or scaled by r to the power 2L. As a result of which, the Kato-Cusp condition becomes, for the density, the log derivative of density at the interparticle, internuclear distance. When you take that to 0, this log density becomes equal to minus 2z divided by bracket L plus 1. So when L is 0, for example, S states, it goes to the Kato-Cusp condition. But when L is finite, it gives you a finite cusp condition value. So therefore, I am able to, by using the density in the manner of scale densities, I am able to extract the information that I need to show that scale density now has information about the location as well as the identity for the entire system in the ground state. Well, cusp condition can be expanded to the excited state, but I will not go into the details of that because there are questions there. Now, so what I do is, I use this as a parameter to talk about energy density relationship. What I do is very simple. It's almost like a textbook kind of a thing. So I take two potentials. One is simple Coulombic hydrogenic potential, minus Z by R. And here, of course, you have the singularity at the nucleus, but then we'll talk about it in other variety or other version of this potential. The hydrogenic Coulomb potential is actually a hard Coulomb potential. It goes like that from minus infinity all the way. It's very hard at the point charge of the nucleus. The other possibility is you do the soft Coulomb or soft core potential. So the denominator becomes R plus beta. So beta is a constant greater than 0. And this is called, in literature, it's called soft core Coulomb potential. So I take two Coulomb potential, the usual hydrogenic Coulomb potential, and then I consider in the part 2 of the work, the soft core Coulomb potential, where I take the general form of soft core Coulomb potential as minus Z divided by, in the bracket, in the denominator, R raised to power Q. Q is greater than 0, all integers 1, 2, 3, 4. So divided, minus Z divided by R to the power Q plus beta to the power Q, bracket close, raised to the power 1 by Q. So Q can go from 1, 2, 3, 4, 5. And these potentials have been, they are model potentials. Q is equal to, one case was introduced by our colleague, senior colleague from IIT Bombay, Professor Patil, Sharad Patil. So it's called Patil potential. And then Su and Eberle and all these people started Q is equal to 2 and so on. Q1, Q2, Q3 of the soft core potential have applications in a large variety of nuclear physics, elementary physics, and so on, including the quantum optics, where Q is equal to 2 potential is used to model the atomic systems under the presence of intense laser fields, whereas Q is equal to 1 for Masonic atoms and molecules, and so on and so forth. So these are all model potential. So part A will consider simple hydrogenic potential. I can consider hydrogenic potential in two different ways in the initial state. One is a free hydrogen atom, other is the spherically confined hydrogen atom of a certain definite radius, where it is actually confined under an impenetrable potential of a finite radius capital R from 0. 0 is the position of the nucleus, a point nucleus. Now, when this position of small r, the coordinate of the electron goes from 0 to infinity for the capital radius R, then it is a free atom. Whereas if I confine it from the large infinite radius R to any finite value, it becomes a compressed atom, and we call that as a spherically confined hydrogen atom. So I will prepare hydrogen atom in two forms, hydrogen free and a finite radius R, and then I will introduce a version which we happen to actually propose, and that was a shell confined hydrogen atom. So it is confined between internal radius R1 and external radius R2. I will tell you what are the advantages of that. So this is how I prepare. Then I put this kind of prepared hydrogen atom in 4 kinds of model potentials which are used to represent the plasma environment around the hydrogen atom. Right? These are all ionic plasma, and they go by the name of Coulomb, Yukawa, and exponentially cosine screen Coulomb potential. You also have one more version where in the Coulomb potential, in all these potentials of screen Coulomb potential, the screening of the nuclear charge is done by an exponential parameter lambda times r. This lambda can be multiplied by 2, then Coulomb becomes double lambda Coulomb. So there are 4 potentials, Coulomb, Yukawa, Coulomb 2 lambda, and ECSC, exponentially cosine screening Coulomb potential. So I'll prepare them and then try to see what does the comparison theorem. There are 3 fundamental theorems in quantum mechanics, as we all know: Hellman-Feynman theorem, Virial theorem, and comparison theorem. Now, comparison theorem about the energies will be used to analyze the energy scale density relationship for cases of hydrogen atom embedded in the 4 plasma potentials, dilute to strong to quantum plasma. Okay, so I'll just use the potentials and see what happens to this relationship. In part 2, I will take the soft Coulomb core potential and change the Q. I'm not putting it in any confined positions, not specially confined, just like that, free soft core Coulomb potential of hydrogen atom. And I will see that as Q changes, again I can use comparison theorem and relate the energy with the scale density and try to analyze how this relationship actually tells us something new. Finally, I will take each of the soft Coulomb core potential, Q1 is equal to 1, and put it in the 4 plasma potential. I will take Q2 is equal to 2, and I'll take Q is equal to 2 and put that into the plasma potential, and so on, and see how energy versus density relationship changes. Now, when I talked about the cusp condition, we talked about the first derivative of density over the density evaluated at the internuclear distance going to 0. That's the first derivative information over the density in the denominator. Now, density in the denominator is also positive things. So, interesting thing is that the relationship that I'm going to talk about has to do with the second derivative. Second derivative. And second derivative of the scale density over the scale density evaluated at the nuclear position will be the density parameter. That is my key parameter that I'm using to define the density in terms of the scale density. So remember, it is a second derivative. So therefore, if this particular ratio is positive, then the numerator is positive because denominator is always positive, rho 0, right? On the other hand, if it is negative, if this ratio is negative, then the numerator, the second derivative, the cusp or the curvature is negative. So these are the information that we will seek, right? So now we proceed just to give the intro. After giving this introduction, let me go quickly. So first presentation was again already this as I showed. The hydrogen atom fundamental Coulomb system provides key quantum mechanical insights. We employ a set of 4 model screen Coulomb potentials in plasma or dielectric with or without spatial confinement, and modify the Coulomb potential given by -1 by R or -Z by R if it is hydrogenic atom. These modifications significantly impact energy levels and electron density as well as the other related structural properties of hydrogen atom. Using the comparison theorem of quantum mechanics for energy, we analyze energy and electron density to derive a rigorous bound on the ratio of the second derivative of scale density to the scale density at the nucleus along the 4 screen Coulomb potential. And in part 2, as I mentioned before, we next consider the family of soft Coulomb potential, where the potential is -Z divided by R to the power Q plus beta to the power Q. Beta is always positive, and it actually shifts the nuclear, shifts the origin, and Q is 1, 2, 3, 4, and we employ the comparison theorem of energy to study the energy density relationship. Finally, hydrogen atom with soft core potentials, Q is equal to 1 and Q is equal to 2, are embedded in a set of 4 screen Coulomb potentials as done for the hydrogen case, and again do the similar analysis. So this is what I'm going to talk about. Then we have the 4, well, we have got the, this is the simple non-relativistic hydrogen Hamiltonian, and the potential is given by this, is a spherical potential. We embed that in terms of, we just superimpose on that Holden potential, which is given by -Z lambda e to the power lambda R minus 1. Lambda is the screening constant. Then Yukawa potential, which is very well known, Yukawa-Debye potential, -Z e to the power minus lambda by R. And then Holden 2, where this lambda is put as lambda, this lambda is put as 2 lambda, and finally exponentially cosines screen Coulomb potential, where the quantum oscillations of the plasma are actually simulated by cosine lambda R oscillation. So these are the 4 potentials that I'm going to use. Now let's see how we can proceed with these things. Before we go that, let me just give you a very brief introduction of the spatially confined hydrogen atom. So this is a model that was given way back in 1938 by Mitchell and co-workers, and this is the model, which is, you have the position of nucleus is here. The electron is now confined inside an impenetrable boundary wall of a radius R, capital R. What we did that, in 2005, we extended that to the shell confined hydrogen atom. And this was just to make all the other possibilities in the spherical symmetry, but you can also have other symmetries, like you can have prolate or oblate and things like that. So then, what are the possibilities of this shell confinement, where you can change R1 and RA and RB, and the electron is confined in the blue space of the shell. Yeah. Then we have this possibility of, well, this is the details of the potential. So one can do the single confinement, as was introduced by Mitchell, by just varying capital R. We can also have, we can put a bubble, like we can have the shell thickness always 1, and the inner radius can move from RA is equal to 1, 2, 3, 4, 5, 6. Each time RB remaining as RA plus 1, RA plus 1, RA plus 1, where RA changes from 1, 2, 3, 4, 5. So it's a bubble that is expanding. So this kind of confinement can be also handled. Then we have also the possibility of the outer radius fixed and the inner radius is compressed from inside. Okay, so this is again yet another kind of a introduction of confinement, spherical confinement can be handled, and we can study the effect of confining the electron densities on a whole lot of experiment, a whole lot of the properties depending upon the density. Then we have the varying outer radius RB and keeping the inner radius constant. So this is one more possibility. So these are all the possibilities that this shell confined model introduces. So we will be doing, we have actually performed computations for both the part A and part B for free, singly confined capital R, and multiply confined RA and RB, which is shell confined. I will present some results, some representative results. So next would be comparison theorem. So comparison theorem in a spherical system says that if there are two potentials, which like V1R and V2R, if V1R Coulombic potential is always more stable than V2R, then the entire eigenspectrum of V1R is also following the same order. This is the comparison theorem. Now, this is a simple comparison theorem, and it holds very well for the set of potentials that we start Coulomb, that is simple hydrogen, then Hulden, Yukawa, Hulden 2, and ECSCP. You can see the energy. This is R versus the potential, and you have here the Coulomb potential will just go like from here, from 0 all the way like that. But you have the minimum one will be Hulden. This is the Hulden, then Yukawa, then Hulden 2, and then ECSCP. So at every R, we can use the comparison theorem for these 4 potentials, a hydrogen atom embedded in these potentials, and then use the comparison theorem. That is, this is the order, therefore the entire eigenspectrum for all levels will follow the same order for all the 4 systems. That is what it is. Now, there are lots of developments on the comparison theorem. It is possible that even if the potentials cross, they are called special comparison theorems. This can be used, and one has to go to the literature to find that out, but then I will leave it at that, and we first go to the next one. And this is the potential. I have just plotted here the potential versus, so here is potential R, and these are the 4 potential, Hulden, Yukawa, the green one is Hulden 2, and the exponentially cosine screen Coulomb potential. And you can see what this computation is at a fixed R. R has been taken as 100 atomic units, which is almost like the free atom. And we have the energies at each lambda ordered according to the way the potential is ordered. So this is energy of the 4 screen Coulomb potentials at different screening constants. And at each point, the ordering remains as is dictated by the comparison theorem. At each point, for a given fixed outer radius, it is 100, which is almost like free, but you can squeeze it. You can put R1 and R2 also. These things are valid all throughout. So I will just try to show now how to relate this to the density in the sense of the ratio of the second derivative of the scaled density to the density evaluated at the nuclear position. So let's go there. So this is what we use. This can be derived by simply putting the wave function that we know as the exact wave function of the hydrogen atom into the Hamiltonian on left and right, collect the powers of R, and then put each coefficient 0, you will get this. So this is what is the result. So the result is introducing the scale density eta for any state as density, 1 electron density divided by R to the power 2L. We get the ratio. This is the first derivative, which is the Cust condition. And the second derivative is what we are interested in. This ratio of the scale density for any spherical potential, which can be written down in this particular form. The form being VR is equal to minus A, capital A is constant, divided by R, plus B, which is a constant, plus a function of R. Function of R is such that as R goes to 0, function of R becomes 0. So if you can recast, or you can imagine the spherical potential in this form, then you get A, B, which are the parameters of the potential, related to the ratio of the second derivative, which is given here on the left-hand side, to the density, scale density at the nucleus. This ratio is the density ratio. This is given by, for all states, 2 by 2L plus 3, A square L plus 1 square, 4L plus 5 plus 2B minus energy. So here is an exact result of energy for this situation for all the potential, spherical potentials, which can be written down as minus A by R plus B plus FR. You can write down this particular exact result, which is stated here. So now, what I'll do is I will use this and try to see what is A and B in the potentials that I'm using. So I will have a relationship between energy and the scale density. I will use a comparison theorem in each case for energy and get an analogous ordering which is dictated by the comparison theorem of energy on the ratio of the energy, scaled energy ratio given here in this form. So let's do that and see what happens. So this is what happens in the 4 cases. This is, well, actually I have not gone there in this slide. This slide is only for the hydrogen atom, free hydrogen atom. For free hydrogen atom, as you know, A is Z, okay, and there is no B, minus Z by R, and FR is that's not there, so only this one. So this particular result, which I mentioned before, this result here, this result A is minus Z, B doesn't exist, so this simplifies to, I take this, so now for hydrogen atom, this is the result. So for, if you take the 1s state L to 0, you get this result. You see the ratio here is such that it is always positive, as a result of which you have the curvature of density near the origin is positive in this case. I'll go further down and see what happens to the situations for the spherically confined situations. Those 4 potentials can be written down again, minus A by R plus B plus FR, and this is what is the result. So this result would be simply for Yukawa, this is for Holden, Yukawa, Holden 2 and ECSCP. And I'll take the energy and write down the energy in terms of this ratio and get the following result, which will be the result which will give me the ordering dictated by the comparison theorem of energy for all the 4 screen Coulomb potentials as Holden plus Z lambda by 2 4L plus 3 is greater than Yukawa, this is greater than Holden 2, it is greater than ECSCP. And for Z is equal to 1, this is the result, and this holds good for any spherically confined or free hydrogen atom embedded in all these 4 potentials. And this we have seen extensively by doing the computations, which is very easy to do. And I'll just give you one result and then go to the next one. So this one would be, so this result is about this is scale density ratio plotted as a function of lambda at a fixed R, and you have an inverse relationship because you see Holden is larger where the Holden was energy wise more stable. V1R was more stable, more negative than the Yukawa, more negative like that, and therefore you get the inverse kind of an ordering for the states of the ratio of the energy density. So you got, this is as Holden, then Yukawa, then Holden 2, and then ECSCP. And at each point of lambda, this ordering is maintained as it should, because the energy gives you the inverse order due to the comparison theorem. That is point number 1. Then I can extend this computations to any R. Keep the lambda fixed and change the R. So if I do that, then I get the situation like this here. That is, well, this is, yeah, this is the other value where you have validation of the comparison theorem for energy on this side, energy versus R, that goes from, R is changed from 3 to 20. You are squeezing from 20 atomic unit to 3 in stages, and you get the result like this is the energy versus for all the 4 potentials, the ordering with squeezing, and this energy in one way for Holden to Yukawa to Holden 2 to ECSCP follows the ordering as dictated in the previous result, which is an exact result for the ratio of the scale densities to every value of confinement at a fixed lambda. So for all valuations of lambda and R, this comparison theorem dictates the order of the energy density which is valid. Now I'll quickly finish in 2 minutes. Soft Coulomb potential. So now soft Coulomb potentials have this very beautiful thing that this is the hydrogenic potential, -1 by R. And then Q1, Q2, Q3, Q4. They order exactly like like tailor-made for application of comparison theorem. At all R, the order remains as higher the Q, lower the energy. At all R. So for any Q, you have a series tailor-made where you can use comparison theorem and go on doing the same analysis. Then following that, you can use each Q as Q1 and Q2 and embed them in any potential, which can be written down in terms of minus A by R plus B plus FR, and then go through the relationship between energy and density and do the same thing. Now, some basic points are the following, and that is that, well, these are all the applications and all the papers. We did this work long time back, but then recently, there has been interest in the one-dimensional soft Coulomb core potential, which is given by one-dimensional thing. This is a 1925 paper in Physical Review E. I have to hurry up now, and this is what we did for soft core potential Physical Review A and Mathematical Physics. We did the conditionally exact solutions, converting that equation to the Hune differential equation, and there are lots of things here, but important thing to note is that we have here this result. For we write VQ, which is this potential, we recast it in this form so that in the bracket when R goes to 0, this FR goes to 0, therefore you only have a B, there is no A. So the second derivative of the scale density to the scale density is given in terms of minus energy and Z by B. It can be shown that this particular energy is larger than this, so bracket term is positive, which gives you a new property to the second derivative, which is negative. So the curvature is now having a maximum as opposed to the hydrogen atom. So this is one. There are many such things. I will not have time to discuss them, but I'll just go on quickly finishing this in the last 2 or 3 transparencies, and that is to say that this is what the relationship would look like when you write for Q. This is the result when you convert into A by R plus B plus FR, and for Q is equal to 1 and Q is equal to 2, this is a relationship. So if you take the numerical values, because eta is negative now, you get this ordering of the scale density. So if the energy of Q2 is lower, then its numerical value of the scale density is less, positive value. So this is what this kind of information of the relationship we can get, and there are some other things that we can discuss, but maybe this is one of the basic things. And finally, well, this is one. Well, the last point would be that the same scale density can be used to, the ratio of the same scale density can be used to talk about the non-sphericity of the density when you have very ultra high magnetic fields on the hydrogen atom, right? Just simple hydrogen atom. So how do we do that? Well, for hydrogen atom, the first part was the result for the state, 1s state. But if you have the magnetic field along a certain z-axis, then you have this particular 3 cosine square minus 1 term. Now, if you average this, that is, this can be calculated using the presence of magnetic field. But the average one can be done by hydrogenic part. So therefore, you can take the difference and then numerically obtain the non-sphericity of the hydrogen electron density in 1s state when you have ultra high magnetic field as found on the neutron stars, for example. So this is done in details, and finally I'll just give you some numbers. So here we see that for the external magnetic field of 1 atomic unit and 10 atomic unit, if you change the radii, you get a certain measure of the non-sphericity. So at constant magnetic field, as you compress from higher side, the non-sphericity decreases, okay? And on the other hand, if you do the fixed R and change from R1, change the magnetic field, it happens that at higher magnetic field, it increases. So these kind of things can be evaluated. So to come back to the final conclusion, the second derivative of the density. In this particular case, the scale density has lot of information which we need to explore. It has not been done. So thank you. Questions are invited.
Swayam Prabha. Digital India. Educated India.